Good morning, everyone. As you may know, designing distributed systems fundamentally requires compromise because asynchronous components are prone to failures and can only see partial global states. We must often choose between incompatible properties. The CAP theorem famously illustrates this by proving distributed database must balance between availability and consistency during network failures. My research focuses on distributed scheduling of parallel workloads modeled as evolving directed acyclic graphs. Like databases, we want distributed schedulers to guarantee ideal properties, to tolerate network and hardware failures, to support elasticity and runtime task submission. But here is the catch. There is no fundamental rigorous mathematical framework mapping out strictly necessary compromise for distributed scheduling. So when such a system fails at scale, it leaves us with the question, is the implementation flawed or is it attempting the mathematically impossible? This is the exact lack of theoretical foundation that motivated the need for proof in my work and led to the approach I will share with you today. My name is Quentin Delamea. I'm a PhD student at Paris-Saclay University, researching alongside Anio, a French leader in high performance and cloud computing. Today, I will show you how I'm specifying and proving Harmonic, the cloud-based distributed scheduling platform at the core of my research using TLA+. I'm doing this using what I call a compositional or modular approach. And this is the topic of the presentation. Before we begin, a quick personal note. I have a significant visual impairment and cannot clearly see the slide while I'm presenting. So if you feel I go off topic or out of sync, please do not hesitate to interrupt so I can reorient myself to the right side. So thank you for your understanding. Specifying and proving a real-world distributed scheduler from scratch is massive. Throughout this talk, I will share with you my practical experience tackling it. First, I'll explain industry's demand for reliable distributed scheduling platform, which is exactly what Harmonica aims to deliver, and why TLA+ is the ideal tool to achieve this. Next, I'll walk you through my modeling process, and I'll explain how I use refinement and composition to first specify core aspects of the scheduling independently before unifying them using composition. And finally, we'll see the practical benefits of this approach that simplify spec review by domain experts, help with model checking, and make formal proof more tractable. So high-performance computing, HPC, is essential across many domains, but it remains notoriously complex. As highlighted by a recent industry survey, the shortage of specialized developers makes this worse. So companies need simpler tools that provide abstraction, that let developers focus on the domain algorithm rather than the intricacies of building a parallel application. And this is exactly what Harmonica aims to provide, a turnkey cloud platform with a simple programming model to design and execute parallel workloads. To illustrate this, here is a Python code for a tiled Cholesky decomposition. This is just a common linear algebra algorithm. Here, as you can see, with Harmonic programming model, you don't need to care about message passing or threads. You only write the code like you would write the sequential implementation and use the task decorator to indicate which parts of your code must run sequentially. That is your unit of code. And then you use the invoke method to tell Harmonica when each task must execute in the flow. Behind the scene, Harmonica builds a directed acyclic graph. Here you have the example for the tiled Cholesky decomposition for a 2x2 matrix. As you can see, this DAG is bipartite. We have two types of nodes, tasks that represent the instance of execution of a compute kernel, and objects that represent inputs and outputs data. Because the DAG is for a 2x2 matrix, it is fairly simple, but for bigger metrics, it explodes and naturally expresses the parallelism of the computation. Then the harmonica scheduler uses this DAG representation to parallelize the execution on an heterogeneous infrastructure, handling, placing tasks, moving data, handling failures, provisioning or releasing resources as the computation needs more or less computing power. One additional detail about this DAG, this is not the case for the Cholesky decomposition, but the harmonic programming model supports dynamic DAGs. That is, tasks can spawn new tasks or even sub-DAG at runtime that reshape the DAG structure at runtime. This feature is needed for some industry use cases like the nested Monte Carlo method. So this is why we implemented it. So harmonica tries to provide all these properties, but reality eventually catches up. At scale, rare failure sequences caused tasks to be trapped in transient state or triggered stochastic errors. Each time we implemented targeted patches to fix the issue, but with each patch come the same question. Is the patch maintaining the internal consistency of the system, of the protocol? Is there a missing failure recovery mechanism? Or some of our failure recovery mechanisms are maybe wrong? Worse, are we attempting something that is mathematically impossible? So we realized that we need rigorous foundation to make sure our system is reliable. This observation led us to shift from our careful, informal development process based on massive testing to a more rigorous one based on formal method. To choose the formal method, we had 4 main criteria. First, because the system is distributed, we needed a language that is well suited for concurrency, that natively supports concurrency. Also, we need an expressive language capable of expressing things, high-level data structures like the DAG, but also the components of the system, the network, message queues, database, etc. Also, because scheduling is related to something eventually happen, the computation eventually progress, we needed a language that supports natively liveness. And finally, as already mentioned in the introduction, we wanted a strong math to ensure that what we are doing is right, and this is why we also wanted a language with a good proof assistant or proof system. To the best of our knowledge, with these 4 criteria in mind, there is almost only one language that is well suited, and this is TLA+. In addition, it is an industry-grade solution that has proven useful in the industry. So we choose TLA+. Right. So we have seen that to make a distributed scheduler reliable, we need a formal method, and TLA+ is the right tool. Now I turn to my modeling process and how I use refinement and composition to decompose the specification. And we'll see later that this approach benefits spec validation, model checking, and formal proofs writing. We started by specifying the scheduling itself. That is, how the DAG evolves over time across user and system actions. Remember, the DAG in Harmonic is made up of tasks and objects. In addition, because the DAG evolves over time, initially independent components may merge. And to manage this, we use the concept of session that define the boundary of a DAG. That is, tasks and objects can be linked only if they are within the same session. So to specify the scheduling, it requires capturing the interactions between the life cycle of each of the 3 fundamental entities, that is, task, object, and session. Instead of specifying everything monolithically using a single specification, we first started by specifying each of these 3 aspects independently using successive refinements, and then compose them to specify the full scheduling system. So this is why I will show you, to keep the focus on the approach rather than the technical code. I won't show you directly the TLA plus code. Instead, I will use diagrams. However, if you like to see the code, it is available on GitHub. Okay, so let's start with the task lifecycle. Initially, the task is unknown from the system. Then it can be created, so it enters the registered state. When the task is ready for execution, it becomes stage. There is an issue. Then, when an agent that is responsible for processing the task is allocated to the task, it becomes assigned. Because of failures or some technical other reason, an assigned task can return to the stage state. When the agent completes the processing of the task, it moves to the process state, and when the post-processing is completed, the task reaches the finalized state. We need additional transitions to bypass the processing in some cases. This will become clear shortly. Even if the specification is very abstract and very simple, it already captures some basic properties of the system. Here are just two examples. For instance, for safety, a task that is assigned if and only if there exists an agent to which it is allocated. For liveness, any task that is processed must eventually be finalized. That is, any task must eventually be post-processed once it has been processed. All this forms task processing 1, the first of our specification. But we can refine the specification to integrate, to capture more the reality more precisely. For instance, the processing of a task may lead to 3 main scenarios. First, the task execution, the task processing may succeed. So the task is succeeded, processing is succeeded. But the processing may fail, but it can be reattempted by submitting a new task that is responsible to execute the same computation. Or the processing may fail, crashes irrecoverably, in which case the task won't be reattempted. For each of these processing scenario comes different post-processing. For instance, a failed task must register a new attempt before transitioning to the retried state. This refinement brings new properties. Here are 2 examples. For safety, for instance, a task cannot be retried indefinitely. And for liveness, a failed task must eventually have its next attempt registered. So all this form the second refinement, task processing 2. But we can refine further with task processing 3 that add some considerations around user action. For instance, a user can postpone the execution of a task by pausing it, or he can stop it. This is a kind of discarding, but with a different post-processing. Just something I lost on the previous slide. The bypass of the processing is used to discard a task ahead of its execution, and this is something we need to propagate errors within the DAG. To fully specify the task lifecycle, we need one more specification, task processing 4, that extends task processing 3 with considerations around task deletion. We can apply the same process for objects, and we obtain 3 refinements, object 1 to object 3, that describe the life cycle of objects. We can do the same for sessions. Sessions are a little bit more simple, so only one specification was needed to capture the life cycle of sessions. All right, but now task, object. So far, we only model task, object, and session independently. However, instances of each of the three aspects are interacting within a DAG. So we need to define the couplings between these life cycles. For instance, a task may transition to stage if all its input data are available. That is, if all its input objects are finalized. On the contrary, an object can be finalized, that is, the data can be written, if at least one of its parent tasks is processed. So, to specify these couplings, we compose the individual specification to obtain graph processing specifications. These are successive refinements of the processing of the DAG, the scheduling of the DAG over time. This new specification bring new property related to the DAG itself. The first obvious safety property is that dependencies between task and object must be a directed acyclic graph that is bipartite and which sources and sinks are objects. We start with data, we finish with data. An example of a liveness property is that when a task crashes irrecoverably, all its descendants will eventually be aborted too, because we won't be able to execute them because one of their parent failed. All the new properties bring by task processing 1 to 4 are properties related to the DAG itself, to its structure. So there are properties about successors, predecessors, ancestors, descendants, because all the other properties have been captured earlier by the independent specifications. Okay, to recap, we have seen that to make harmonica reliable, we need TLA plus to achieve this. We just seen how to decompose the spec to specify the whole system step by step, and now we'll see the practical benefits of this approach. First, a specification is valuable if both it is mathematically correct and it is faithful to the real system it models. To ensure faithfulness of my specification, I hold weekly review sessions with the harmonica development team to be sure that what I modeled, what I specified, is what the engineers want to have in the real software. The fact is that initially, the development team had no prior experience with formal methods. So this approach of decomposing step by step helped the team because we started with simple focused specification. And this helped the team to build experience gradually and to be able to read more and more complex specification as the specification continued. Let's talk a little bit about model checking. Model checking is challenging, first because we have the famous problem of state space explosion. There is no real universal solution to it, but a common approach to alleviate this is to use symmetry reductions. That is, the symmetries within, we use the natural symmetries of the system to reduce the state space. However, this approach, this method is incompatible with liveness checking. So when we use symmetry reduction and we want to prove the safety property, we have no prior check on the safety property. The second challenge is formula evaluation. In enabling conditions or properties, we use mathematical formulas that can be costly to evaluate by the model checker. To address this issue, there are two common approaches. The first is to rewrite your code in a more model checker friendly approach. For instance, using recursive formulation instead of existential ones. But the inconvenience is that this encourages computer-oriented coding and the resulting formula may be harder to manipulate for the proof. The other approach is to use a Java overload, that is to replace an operator by a Java code. This may be very efficient, and of course I needed it for some of my spec, but it introduced black boxed code, so the real math is not checked by the model checker, and then when you come to the proof, you have no prior check on it. And in addition, this may introduce errors because Java code is less rigorous than TLA+. So all this mitigation should be used as less as possible, only when we really need it. The thing with the modular approach is that the first specifications are fairly simple because they are focused on only one thing. For this reason, we can check many properties early. We start also with specifications that are simple, so less concerned by the state space explosion. So with a modular approach, you can postpone this mitigation to the specification that really need these optimizations. So this is one of the benefits of this approach. The last benefit is about the proofs. By decomposing the specification, we also decompose the proofs themselves. In fact, first specifications are fairly simple, so proving them is almost trivial. That was so easy that I shifted from by just using the model checking on the first specification just as a sanity check before writing the proof. And then for the composition, the proof are of course a little bit harder, but the approach also helps to do it step by step, and all the results that we prove in the first specification can be reused to prove other results in the subsequent refinements. Indeed, we still have to prove the refinement property, and this is maybe sometimes this is the hardest part. Sorry. Okay. Time to conclude. What we have seen is that to make a reliable distributed scheduling platform like Harmonic, we need formal methods, and TLA+ is the right tool. We have seen that we can first specify independently the core aspect of the system and using successive refinement, and then use composition to unify them to specify the full system. This approach has benefits. It helps with spec review, model checking, and it makes formal proof more tractable. The next step is first to complete this first specification phase to prove the remaining specification, and then to model the rest of the system. What I showed you is almost the interactions on the central database of the Harmonica system. But to have the full picture, we need to model all the other components and the interactions and make sure that even in case of failure, everything is working consistently. Thank you for your attention, and I would be happy to answer any question you may have.